Imagine waking up tomorrow morning and reaching for your smartphone to check the time. You open your GPS navigation app to plan your route to work, perhaps past a nuclear power plant that provides electricity to your city. What if I told you that none of these everyday technologies would function properly without the groundbreaking theories of one man who lived over a century ago? Albert Einstein, a name that has become synonymous with genius itself. When we think of Einstein, we often picture the wild-haired professor scribbling complex equations on a blackboard, his tongue playfully sticking out in that famous photograph. But Einstein was far more than just a theoretical physicist lost in abstract thought. He was a visionary whose revolutionary ideas about space, time, matter, and energy have fundamentally transformed our modern world in ways that would have seemed like pure science fiction to his contemporaries. Today, more than 60 years after Einstein's death, his theories don't just sit gathering dust in university libraries. They're actively working in the palm of your hand, powering the satellites orbiting above us and generating the energy that lights our cities. From the GPS system that guides your daily commute with pinpoint accuracy to the nuclear reactors that provide clean energy to millions of homes, Einstein's insights into the nature of reality have become the invisible foundation upon which our technological civilization rests. But here's what makes this story truly remarkable. When Einstein first proposed his theories of special and general relativity in the early 1900s, they seemed to contradict everything that humanity thought it knew about the universe. Time wasn't constant. It could slow down or speed up. Space wasn't fixed. It could bend and warp. Mass and energy weren't separate entities. They were two faces of the same cosmic coin, connected by that most famous equation in all of science, E equals mc squared. These weren't just abstract mathematical curiosities. Einstein was revealing fundamental truths about reality itself, truths so profound and counterintuitive that even today they challenge our everyday understanding of the world around us. Yet without these seemingly impossible ideas, our modern technological landscape would look drastically different. Consider this. Every time you use your smartphone's GPS to navigate to an unfamiliar destination, you're relying on Einstein's prediction that time moves differently depending on your speed and gravitational environment. The satellites orbiting Earth experience time slightly differently than we do on the surface, and without accounting for Einstein's relativistic effects, your GPS would accumulate errors of several miles every single day. What seems like magic, knowing your exact location anywhere on Earth within a few feet, is actually applied Einsteinian physics. Or think about nuclear energy, which provides approximately 20% of America's electricity and powers submarines beneath the oceans. Every nuclear reaction, whether in a power plant generating clean electricity or in the nuclear medicine that saves lives in hospitals around the world, is a direct demonstration of Einstein's most famous insight. That matter can be converted into energy according to his revolutionary equation. Today, we'll embark on a fascinating journey to discover how Einstein's seemingly abstract theories have become the practical technologies that define our daily lives. We'll explore how his insights into the nature of time and space keep our global positioning systems accurate, how his understanding of matter and energy powers our cities and heals our bodies, and how his theories continue to open new frontiers in computing, communication, and space exploration. This is the story of how one man's revolutionary thinking about the fundamental nature of reality became the technological foundation of the 21st century, and how Einstein's legacy continues to shape our future in ways we're only beginning to understand. Let's begin our exploration with perhaps the most remarkable example of Einstein's theories at work in our daily lives: a technology so seamlessly integrated into our modern existence that we rarely stop to marvel at its incredible complexity. Every time you pull out your smartphone and ask it to guide you to the nearest coffee shop, you're witnessing one of the most sophisticated applications of relativistic physics ever deployed on a global scale. The Global Positioning System, GPS, consists of a constellation of 31 satellites orbiting Earth at an altitude of approximately 12,000 miles, traveling at speeds of about 8,600 miles per hour. These satellites are essentially flying atomic clocks, each one broadcasting precise timing signals that your device uses to calculate your exact position anywhere on the planet. But here's where Einstein's genius becomes absolutely crucial. Those satellites experience time differently than we do here on Earth's surface. According to Einstein's special theory of relativity, time slows down when you're moving at high speeds relative to an observer. Since GPS satellites are racing around Earth at tremendous velocities, their onboard clocks should theoretically run slower than identical clocks on the ground, by about 7 microseconds per day. 7 microseconds might sound insignificant, but in the world of GPS precision, it's enormous. Light travels about 1 foot in a nanosecond, so even tiny timing errors translate into massive positional mistakes. But Einstein's general theory of relativity adds another layer of complexity to this cosmic puzzle. According to general relativity, gravity affects the flow of time itself. The stronger the gravitational field, the slower time moves. Up in orbit, GPS satellites experience weaker gravity than we do on Earth's surface, which means their clocks actually run faster than ours, gaining about 45 microseconds per day compared to ground-based clocks. Now here's where the mathematics becomes beautiful. These two relativistic effects work in opposite directions. The satellite's high speed makes their clocks run slow by 7 microseconds per day, while the reduced gravity makes them run fast by 45 microseconds per day. The net result? GPS satellite clocks gain approximately 38 microseconds every single day compared to clocks on Earth. 38 microseconds per day. What would happen if we ignored Einstein's predictions and didn't account for this relativistic time dilation? The errors would accumulate catastrophically fast. Within just one day, your GPS would be off by about 38 feet. Within a week, the error would grow to over a quarter of a mile. After just 1 month of operation, GPS would be so inaccurate that instead of guiding you to your destination, it might direct you to a completely different neighborhood entirely. This isn't theoretical speculation, it's been tested. In early GPS experiments, engineers temporarily turned off the relativistic corrections to see what would happen. The results were exactly as Einstein's theories predicted: rapid, dramatic degradation of positioning accuracy that rendered the system completely useless for navigation within hours. But because we do account for Einstein's relativistic effects, GPS works with almost magical precision. The system can pinpoint your location to within 3 to 5 feet anywhere on Earth's surface. This extraordinary accuracy enables not just navigation, but an entire ecosystem of location-based technologies that have revolutionized everything from emergency services to agriculture, from ride-sharing apps to scientific research. Consider the broader implications. Every Uber ride that finds you precisely at your location, every emergency responder who can locate accident victims with pinpoint accuracy, every farmer using precision agriculture to optimize crop yields, every scientist studying earthquake patterns or climate change. All of these applications depend fundamentally on Einstein's insights into the nature of space and time. The GPS system represents something truly extraordinary in human history, a technology that requires us to account for the fundamental structure of space-time itself just to function properly. Every day, Billions of people carry in their pockets a device that must constantly perform relativistic calculations that would have been incomprehensible to scientists just over a century ago. And this is just the beginning of our journey through Einstein's technological legacy. As remarkable as GPS is, it's only one example of how his revolutionary understanding of reality has become woven into the fabric of our modern world. While GPS demonstrates Einstein's theories working with exquisite precision in the realm of time and space, perhaps no application of his insights has had more profound consequences for humanity than nuclear energy. Here we encounter what is arguably the most famous equation in all of science, E equals mc squared, an elegant mathematical expression that unlocked the most concentrated source of energy known to physics. Einstein's mass-energy equivalence principle revealed something extraordinary about the nature of reality itself. Mass and energy are not separate entities, but different manifestations of the same fundamental quantity. A tiny amount of matter, when converted completely to energy, releases an almost incomprehensible amount of power. The c-squared in Einstein's equation, the speed of light multiplied by itself, is an enormous number, approximately 90 trillion meters squared per second squared. To truly grasp the magnitude of this relationship, consider that converting just 1 gram of matter, roughly the mass of a paperclip, into pure energy would release the equivalent of 21,000 tons of TNT. This is the theoretical maximum, but even the partial conversion achieved in nuclear reactions produces energy outputs that dwarf anything possible through chemical processes. In nuclear power plants around the world, Einstein's equation governs every moment of operation. Inside the reactor core, uranium-235 nuclei undergo fission when struck by neutrons, splitting into smaller fragments. During this process, a small amount of the original mass disappears, not destroyed, but converted into energy exactly as Einstein predicted. The missing mass becomes kinetic energy of the fission fragments, radiation, and the energy that ultimately heats water to drive steam turbines and generate electricity. The numbers are staggering. A single uranium pellet the size of a fingertip contains as much energy as a ton of coal. One nuclear fuel assembly can power thousands of homes for years. Currently, nuclear power plants generate about 10% of the world's electricity, providing clean, carbon-free energy that helps combat climate change. Countries like France derive over 70% of their electricity from nuclear power, demonstrating the practical scalability of Einstein's theoretical insights. But Einstein's mass-energy relationship extends far beyond terrestrial power generation. Deep in space, the same fundamental principle powers the stars themselves. In the core of our Sun, hydrogen nuclei fuse together to form helium in a process that converts approximately 4 million tons of matter into pure energy every single second. This stellar fusion, governed by Einstein's equation, has been lighting and warming our planet for billions of years and will continue to do so for billions more. Scientists and engineers are working to harness this stellar process here on Earth through controlled nuclear fusion. Experimental reactors like ITER, the International Thermonuclear Experimental Reactor, represent humanity's attempt to create miniature stars in magnetic bottles, fusing light elements like hydrogen and helium to release clean, virtually limitless energy. When fusion power becomes commercially viable, it will represent the ultimate application of Einstein's insights, powering human civilization with the same fundamental process that powers the cosmos. The medical applications of nuclear physics provide another profound example of Einstein's legacy saving lives daily. Nuclear medicine relies on radioactive isotopes that decay according to Einstein's mass-energy principles, releasing precisely controlled amounts of radiation for both diagnosis and treatment. PT scans use positron emission, a process where matter and antimatter annihilate completely, converting their entire mass to energy as Einstein's equation predicts, to create detailed images of metabolic activity inside the human body. Cancer treatments using targeted radiation therapy depend on our understanding of how atomic nuclei release energy when they decay. Radioisotopes like cobalt-60 and cesium-137 provide precisely calibrated energy sources that can destroy cancerous tissue while minimizing damage to healthy cells. Millions of patients worldwide have benefited from these applications of nuclear physics, each treatment a practical demonstration of Einstein's theoretical breakthrough. Yet Einstein himself was deeply conflicted about these applications of his work. Though his letter to President Roosevelt helped initiate the Manhattan Project, Einstein later called it the one great mistake of his life. He understood that the same principles enabling clean energy and life-saving medical treatments could also create weapons of unprecedented destructive power. This duality, the potential for both creation and destruction inherent in fundamental scientific knowledge, represents one of Einstein's most complex legacies. The equation E equals mc squared doesn't distinguish between peaceful and military applications. It simply describes a fundamental truth about the universe that humans must choose how to apply. As we stand on the threshold of the fusion age and continue developing new applications of nuclear science, we carry forward both Einstein's scientific genius and his moral concerns about the responsible use of knowledge that can reshape the world.